Now we are going to concern ourselves with this diffusion process from the bulk fluid through a viscous sublayer to our external catalyst surface. If you need more background or you feel you need some revision on diffusion processes, a very good summary given in your textbooks in the pages listed here. Important for our application to note is that we are going to consider this flux, the diffusional flux, in only a single direction. How can we manage that? We pretend that this viscous sublayer is so thin that I can actually cut it open here, I can make a little cut, and I can roll it flat so that it ends up looking like a flat surface with diffusion only in one dimension, and that is through a boundary layer with a thickness delta. Another important thing is to pay attention to the units of that diffusion process. So as it's derived, it will give us a flux. So a flux tells us that it's got units of how many moles of A diffuses per second to a specific area. And that area will always be my external catalyst surface area that I can calculate using AM if I want it in units of meters squared per kilogram catalyst. This flux depends on a rate constant, a flux rate constant, and the driving force that drives diffusion. And that driving force is the difference between the bulk phase concentration and our surface concentration. Pay attention to the details of this derivation for how we get to this equation. What is also important to note is what affects this rate constant. It's got two important parameters. The first is what is the rate of diffusion, molecular diffusion of A as it diffuses through the mixture that constitutes that viscous boundary layer, divided by the thickness of the boundary layer itself. This rate constant, we use the subscript C, K subscript C, to denote that we are talking about the external diffusion rate to that catalyst surface. So if we consider that this is a flux that gives us moles of A diffusing per second per meter squared external catalyst surface, inherently what we must realize is that Kc is a K double dash kind of rate constant. It is based on the external catalyst surface area. So I can now say the rate at which A disappears, and that's why I've got the negative here, from my bulk. Why does A get removed from my bulk? Is equal to a rate constant multiplied by a driving force for that diffusion rate. And here I have converted my Kc, which is an area-based rate constant, by multiply to a volumetric rate by multiplying it by that appropriate parameter. So I've got the Ra here without any dashes to indicate that I want the volumetric rate, and therefore I need the appropriate volumetric rate correction factor. If I now consider a small little control volume, and I draw it differently, so I just draw it there where it hits the viscous sublayer. I've got stuff coming in due to bulk transport. I've got stuff leaving due to bulk transport, but I also have a rate at which it leaves my control volume, and that is equal to the rate of this flux multiplied by the appropriate conversion factor, and in this case I'm interested in the volumetric rate of disappearance. If I now, for instance, are considering a CSTR, my mole balance would be Fa that comes into that control volume multiplied by Fa that goes out of that control volume plus that flux multiplied by the appropriate conversion factor multiplied by the volume of my reactor, which under steady state conditions must still give me 0. And instead of this flux, I can now substitute min Kc times Ca bulk minus Ca surface, which gives me the area-based rate at which stuff will disappear from my rate control volume due to diffusion into that boundary layer. What specifically interests us in this theme is which parameters will influence this rate constant. Whether it is now a constant that I am going to convert to be a mass-based rate constant, and then I must remember to use the appropriate units, or this volumetric-based rate constant. What can I do in order to make this factor so large that this driving force can become really small, and that I can approach the bulk phase concentration at my surface, so that the difference between my bulk and the surface where the reaction can actually take place becomes small. That will only happen if this rate constant becomes really large. The diffusivity. In molecular diffusivity, we get different correlations that you can use to calculate this molecular diffusivity. And that you will see is affected by the viscosity of your fluid, the density of the fluid. So what will affect it? Of course, the mixture composition, and to a very limited degree, the temperature. So this is not as temperature dependent as you think. Yes, it may increase with an increase in temperature for liquids. For gases, it may actually decrease with an increase in temperature, but it's got a linear, very low slope temperature dependence. This thickness of the boundary layer, I can affect by having much smaller particles in my reactor. That will give me thinner and thinner thickness layers, therefore my rate constant will continue to increase, or I can increase the shear in my reactor. If I have a CSTR, I can increase my stirrer speed to make this boundary layer thinner. In a packed bed reactor, I can increase the linear velocity. And how do I do that? Of course, I manipulate my tube diameter so that I've got higher linear velocities in my reactor. To illustrate the dependence of this Kc parameter. So remember, Kc includes the molecular diffusivity and the thickness of the layer. Some correlations, so lots of empirical correlations available for calculating Kc. The one that I show here, the Teunis-Kramer correlation, is specifically applicable to packed bed reactors. Please do not apply this relationship to CSTR reactors. It's derived for external diffusion area-based rate constant in a packed bed reactor. What is important here, yes, you will be able to use this when you evaluate your designs in CPJ. More important is the proportionality of Kc to the different parameters in your reactor that you have control over and those that you do not have control over. At that, we are going to use this for proration applications. So first off, the physical properties of your fluid. This is the stuff that you don't have control over unless you manipulate the temperature. So we've got some fighting effects. Once again, we've got the density, and it's inversely proportional to the viscosity and the molecular diffusivity. All of these will be mildly dependent on the mixture composition and very mildly dependent on the temperature. In some correlations or in some textbooks, I think Vogler is one of them, they actually say that Kc, if you apply this Teunis-Kramer correlation, is pretty much directly proportional to temperature to the power of a 6. So that's a very weak temperature dependence of Kc because of this fluid properties on which it depends. These two parameters, the linear velocity in your packed bed and the particle size of the catalyst that you choose, is in the control of the design engineer to a limited extent. Of course, the linear velocity, you can have your total mass flow that goes into your reactor, and you can have it in one big single tube, or you can divide it into 4 smaller tubes where the linear velocity will be high, or you can have 50 of those smaller tubes, exactly the same diameter, and the linear velocity between the two will decrease, or I can have thinner tubes. So in fact, the geometry of our reactor will significantly affect this rate constant that determines whether we are going to have external diffusion limitations in our reactor or not. For CSTR and batch reactors, once again, please just be warned that you should not use the Tiernes-Kramer correlation, which was specifically derived for packed bed reactors, where you have this linear velocity that you can calculate by considering the reaction geometry. Rather, in these two reactors, no single correlation exists that can describe Kc. It depends on what is the size of my reactor relative to the size of my impeller. What type of impeller do I have? Do I have a little magnetic stirrer there at the bottom of my reacting mixture, or do I have a paddle type impeller that can turn the fluid in my reacting mixture? Did I include some baffles? Does my design come with some baffles that is fixed in my reactor bed in order to improve the rate of mass transfer and subsequently increase the value of Kc? All that we can subsequently say about this flux rate constant, this per area of my external area of my catalyst rate constant in a CSTR and a batch reactor, is that it is directly proportional to the stirrer speed, but to some unknown factor n. Just on a side note over here, and I've had some confusion in the past, that n is not related to my actual true reaction order. So if I have 2A that goes to B, and I tell you that it's an elementary reaction rate, and you can say therefore my Ki, if I have the intrinsic rate, it is Ca as it is at the surface to the power of 2. That and that n is not the same. So that is an independent parameter that just says how does my Kc change with the RPM in my reactor. And then of course it will also be affected by the particle diameter. The smaller the particles always, if I have smaller particles, the thickness of the boundary layer will go down, and subsequently my Kc value will go up. But to which extent depends on the shape, the size, the geometry, the layout, the stirrer type in your CSTR or your batch reactor. If we now consider steady-state flow reactors, and of course we are going to limit our discussion on the steady-state flow reactor behavior. We are going to have our 3 layers once we've rolled our catalyst particle flat. We've got our bulk, in which we have our bulk phase concentration. This is the concentration and the flow rates that we are going to use to calculate conversion. We've got our stationary boundary layer through which diffusion takes place. And then we've got our catalytically active surface where the rate of the reaction can take place. For now, whether we have a solid catalyst or a porous catalyst, the analysis is exactly the same. We are going to assume that for our porous catalyst, internal diffusion doesn't exist, and as soon as it hits that surface, it can actually get access to the entire inside of my catalyst particle. When I now perform my mole balances, I can actually consider 2 different control volumes. First, that red control volume that I considered on the previous slide that says, why does stuff disappear from the bulk? It disappears if I consider the red control volume because it diffuses into this boundary layer, and then it's not present in the bulk where I calculate my conversion. In other words, I can now, for a CSTR, this is the red control volume mole balance that I can write. And here I've written that rate at which it disappears in terms of my mass-based flux rate constant. So I've used AM, which is the meter squared per kilogram catalyst, and because I wanted to use the mass of catalyst that is present in my reactor as my independent variable. So for my CSTR, that denotes the mole balance when I consider the red control volume. When I consider this yellow control volume, so I can actually extend my boundary to say, all right, why does stuff disappear from the bulk? It disappears because it participates in the reaction catalyzed by the catalytically active sites on my catalyst surface. And therefore, the rate equation I must use there must have the surface concentration as the concentration at which the actual reaction rate occurs. So here it is my traditional mole balance that we always wrote for the CSTR reactor, the mass-based one, therefore the Ki dash, except that in my rate equation for this nth order reaction, I must now substitute the surface concentration and not the bulk phase concentration, because that is the concentration that's relevant and that is exposed to the catalytically active sites where it can react. Of course, if I want steady state conditions, this left-hand side of both of my mole balances must be equal. And the implication is that these two rate processes under steady state conditions must be equal to each other. Otherwise, I will have a buildup of Ca surface over time, or I am going to see a depletion in Ca bulk over time, and I will not have steady state conditions. I can apply a similar mole balance for my packed bed reactor that I used to show that these two equations must then be equal, where I can say stuff disappears from the bulk. Remember, when I'm going to integrate this, I'm going to integrate over the bulk phase molar flow rates. Stuff disappears from the bulk because of the chemical reaction that takes place, governed by, and that rate is governed by the surface concentration and the order of my reaction rate. And that must be equal to the rate at which I can supply the stuff to that surface of my active catalyst. This allows me to, depending on the basis, am I doing it per reactor volume, per kilogram catalyst, or per active external area in my catalyst surface, this allows me to set up, this is actually just one equation on different bases, but I've got an extra equation available. And that is, of course, very handy because we've got an extra unknown in our mole balance equations, regardless of whether we use version 1 or version 2 of our mole balances. We set them equal to each other in order to derive this extra equation that can help us solve for that extra unknown, which is the concentration of my reactant at the catalyst surface.